So, in my last class I talked about this representation of bounded operators in terms of this displacement operators, right. And then I also talked about that I mean so there is a connection between these bounded operators. So, f is bounded and square integrable functions, right. This f of alpha is square integrable. In the sense that I can write f as 1 upon pi alpha belonging to C d square alpha trace over f d alpha then d of minus alpha, right. So, this we have discussed and we have seen that so this is my f alpha. Now, the question is that it may happen that this is bounded operator, still this f alpha can be singular. For some alpha, right. It does not mean that this is not square integrable. So, this can happen, right. So, so the question is for what sort of operators this will be also non singular, this is finite, and one can show that if this is trace class, okay. So, trace class means that f 2 which is trace of square root of f dagger f. If this is finite, then this is trace class, and for trace class operators one can show that this f which is the weight function, this is also finite, there is no singularity, okay, right. And because for bounded operator itself there can be singular weight function, if you consider these to be unbounded operators, then of course this will be even more singular, okay. So, let us take this example where f is equal to the displacement operator. So, this is of course, this is not a bounded operator, right. Displacement operator is not a bounded operator because if I take this norm which is square root of trace of f dagger f, this is infinity. So, this is unbounded operator, okay. This is unbounded, and therefore, it cannot be trace class. But if I look at this norm which is the least upper bound over all psi such that this is normalized psi f dagger f psi, maybe you will have to take the square root of that, okay. Then for this operator this should be equal to 1, right, because this is unity identity operator.
No, only for alpha is equal to 0 its identity.
Alpha is equal to 0? No, for any alpha it is identity.
For any alpha it is identity operator.
Yes.
F dagger d alpha is the unitary kind of.
Oh, I thought d alpha is you are saying d alpha is identity.
No.
Side of that, F dagger
F and d alpha dagger d alpha is identity because it's
Okay, yeah.
Yes. So, this is identity, right. This is identity operator. So, therefore, this is equal to 1. So, therefore, this means that f is a finite operator according to our definition. It is unbounded, but finite operator. Okay. So, now what about its weight function? So, if I look at trace of f d alpha which is okay, I have taken d, maybe let me call it as d beta, okay, which is f of beta. So, this is trace of d alpha d beta, and now I think we have done it earlier that this is equal to trace of d alpha d of minus beta, then inverse of that, okay, and this is nothing but pi times delta of alpha minus beta. So, alpha plus beta, right. Okay. So, this is the f beta weight function, and this is of course singular. Okay. So, this is unbounded function although finite, but and therefore, it is it is no wonder that its weight function is singular. Okay. Right. But this is a bit tricky issue. So, what does it mean? It means that if I take the displacement operator basis, then expressing unbounded operators in terms of displacement operator basis is not a good idea, because you will then encounter this kind of singularities, right. So, better you take some other operator basis, and as I told you, these operator bases are important to describe phase space distribution functions, different types of phase space distribution functions. So, I need to consider another kind of operator basis in which such unbounded operators can still be useful. Okay. So, this is what I am going to describe now. Is it clear? Okay. So, what I will do is I will consider operators. So, f is of course bounded operator, I mean it can be bounded, it can be unbounded, but this I know that I can express it in terms of this square alpha, this square beta, this is alpha f beta, then this is alpha beta, right. So, basically we are expressing this f in terms of this operator basis, okay. And you know that these operators are, these are not only bounded operators, these are trace class operators, these are trace class operators. Okay. So, you are expressing f in terms of trace class operators, right. Okay. Good. So, this is, you can call it as a coherent state representation. Okay. Right. And from here you can figure out that this f, which is basically trace of f dagger f, this is as simple as this is 1 by pi square alpha beta belonging to C alpha f beta square, this square alpha, this square beta. So, basically it depends upon this kind of function, integrability, square integrability of this function. Okay. So, if this is square integrable, then of course f is finite. If it is not, then f is if it is square integrable, then f is bounded. If it is not, then of course it can be unbounded. Okay. Right. Okay. Good. So, if I look at this function, generically you know, this will not have singularity. If f is a bounded operator, this will not have singularity. I mean, if f is unbounded, there can be some cases where this is singular. Okay. So, generically this is for bounded operator, there is no singularity here. Okay, good. And one can prove that, you know, this is finite. So, so f is finite. What does it mean? As I said, this means that this norm is finite, right? And it is easy to show that this is less than equal to f because of, you know, our properties. So, therefore, f is finite means that this is also finite. So, there is no singularity in this case. Okay. So, f finite means this is, there is no singularity here. What about
last equation come?
Okay, good. So, you know, what is the definition of f?
It has same sign on the both sides.
Yes.
So this is not the same thing.
Yes, but what is the what is this one?
Offline element should be smaller than.
No, this is automatically true. You use the Schwarz inequality, this is automatically true.
Okay.
Because there it is expectation value of f dagger f with respect to psi. Okay. So, this is always valid. So, therefore, f is finite means this has no singularity. Okay. Right. Okay, then. So, this is what I just wanted to say about these operators and their properties. So, let me once again come back to this ordering of the operators, because from there we can go to these different representations.
So we are still looking at that first paper that last year.
First paper, and then so today I will complete, well, I am not going to complete that. What I will do is I will mention the main results and then I will go to the next paper. Okay. Yeah. Okay. So, now if I look at these, so what I will discuss now is this ordered representation. Okay. So, ordered operators, this we discussed earlier also, but now we will have to do it in more systematic manner. Okay. So, f is again bounded operator. As I said, you know, if it is unbounded operator, then things will be much more difficult and there will be lots of restrictions. So, in general I will consider bounded operators. Okay. Right. So, then we know that this is the case. In terms of displacement operators, and this is of course square integrable, this weight function. Okay. So, if I look at the normal ordering, which means that f can be written as n m is equal to 0 to infinity c n m a dagger to the power n a to the power m. So, these are the coefficients. Question is that given f, I mean, how will you get this expression? In other words, how will you get these coefficients? Okay. Is there a prescription for that? Okay. So, this is what we are going to discuss now. Okay. So, this you know that this can be written as 1 upon pi alpha belonging to C d square alpha trace of f d alpha. Now, I use this Hausdorff-Campbell formula, okay, for the normal ordering. So, what is that? e to the power minus mod alpha square by 2. Okay, so you know that this is d of minus alpha is equal to exponential of what is this minus alpha a dagger plus alpha star a, right. So, you can use this this formula, Campbell-Hausdorff formula, alpha a dagger into e to the power alpha star a, right. So, this you can use. Okay. So, now this is simple, you can use the series form. So, this is n m is equal to 0 to infinity a dagger to the power n, what is this, yes, divided by n factorial a to the power m divided by m factorial, okay. Then 1 upon pi alpha belonging to C d square alpha trace of this is f d alpha into e to the power minus mod alpha square by 2 into minus alpha to the power n alpha star to the power m. Okay. Is that correct? Yes. So, therefore, you can compare with this. So, what will be your Cn? So, basically Cn m will be equal to 1 by n factorial m factorial 1 upon pi alpha belonging to C d square alpha trace of f d alpha, then this is e to the power minus mod alpha square by 2 into minus alpha to the power n into alpha star to the power m. So, this is the basically the expression of this coefficient. Okay. And now, if you look at here, because this is square integrable. So, this does not have any, let us say, singularity, okay. Because of this the exponential here minus of this. So, you can understand that these are all finite, okay. Unless this is a very ill behaved function, these are all finite because of this exponential.
It will not have singularity only when it is f is trace class, right?
Yes. No, for trace class it will not have singularity, yes.
But if it is bounded, f is bounded, then it can have singularity.
Yes, but you have this factor also. So, the question is, this is integral is there. So, therefore, even if it does have singularity at some point.
Anyway, the integration has been done.
Yes.
At some point it will have this thing.
Yes.
But globally it will.
Yes. So, because this will be basically in general a finite quantity. Okay. So, in fact, what you can prove is that. So, let us look at the CNM mod square. So, this is what? This is basically is 1 upon n factorial m factorial square into 1 upon pi, this is alpha belonging to C d square alpha. So, let me call it as less than equal to. So, this is trace of f d alpha mod square times this is 1 upon pi integral beta belonging to C d square beta. Well, you can take alpha also, it does not matter. So, then e to the power minus mod beta square into so mod of this. So, basically what you will get is beta to the power twice n plus m. Is that a correct statement? Yeah, again you use Schwarz inequality basically. Okay. Yeah. So, this part we know, this is your norm of f square. what about this part? So, this is something like your gamma function. Okay. Right. So, basically what you will have is this thing is your n plus m factorial. Yeah, I think gamma function, if you do, this is what you will get. Okay. So, as a result, what you will see is that the C n m mod is less than equal to n plus m factorial whole to the power half divided by n factorial m factorial into norm of m. Okay. Right. And you see that because if this is finite for bounded operators, this is also finite. Okay. Right. Okay, good. So, yeah, this actually you can show that this just you will have to change the integration and do that. This will be a gamma function. This is what is known as gamma of n plus m plus 1, right. Yeah. Okay. Good. So, therefore, for normally ordered operator, of course bounded operator, you have these expression for the weight the coefficients, and also these are finite. Now, let us look at anti-normally ordered operators. So, f is anti-normally ordered, n m is equal to 0 to infinity d n m a to the power m a dagger to the power m. So, this is my anti-normal ordering. Okay. So, again you can use this expression, this time you will have to use in terms of e to the power mod alpha square by 2, and then this is e to the power, what will be this? So, this is exponential of minus alpha a dagger plus alpha star a, right. So, what you need to have alpha star a e to the power minus alpha a dagger, okay, right. So, once again if you do this thing and compare with this, what you will get is the following. So, you will get that d of n m, these coefficients, these are 1 upon n factorial m factorial into 1 upon pi alpha belonging to C d square alpha trace of f d alpha, then e to the power mod alpha square by 2 plus mod alpha square by 2 minus alpha to the power n alpha star to the power m. So, from here you can see that even if this is finite, because of this exponential, this will have singularity. Okay. Okay. So, generically this, even if this is a bounded operator, this can have singularity. Okay. Now, let us look at the symmetric ordering. So, f is equal to n m is equal to 0 to infinity b of n m. Now, I take symmetric ordering. So, I told you what do we mean by symmetric ordering, right. So, this is symmetric ordering. So, this is in the sense that, for example, if I take a dagger A, then this is half a dagger A plus A dagger. If I take A dagger A square, then this is 1/3 A dagger A square plus A dagger A plus A square A dagger. So, in that way, you know. So, this is your symmetric ordering, right. Okay. So, for symmetric ordering, how to get this coefficient? So, therefore, you see that let us look at again this expression. So, let me erase this part. So, this will be basically so this is just you take the series n is equal to 0 to infinity minus alpha A dagger plus alpha star A to the power n by n factorial. Okay. So, you just take this series. Okay. So, if I look at this term, it is symmetric ordering. Okay. And if you look at these examples, you see that there are basically n plus m factorial by n factorial into m factorial. There is many number of ways of ordering such a term, right. If you go back to your this permutation combination classes, this is what you will have. Okay. Like here, if you take the n is equal to 1, m is equal to 2, then you will have factorial 3 divided by factorial 1 into factorial 2. So, therefore, this is 3. So, 3 ways of ordering. Okay. And
n plus m
yes,
variables.
yes,
And n of them are similar and okay.
exactly, exactly. So, that is the way you will have to do that. So, basically you put them in a box, okay, similar things in a box. Okay. Okay. So, basically if you expand it like this, it will have these many terms. Okay, good. So, as a result, what you can look at is this minus alpha minus alpha A dagger plus alpha star A. Oh, maybe I have minus alpha A dagger plus alpha star A. So, this is the term. What you will get is this thing r is equal to 0 to n factorial divided by r factorial n minus r factorial. Okay. Now, this is minus alpha to the power r, then alpha star to the power n minus r into this symmetric ordering A dagger to the power r, A to the power n minus r. Okay. How do you get that?
Binomial expansion.
Yes, binomial expansion. This is okay. This is what you get in binomial expansion. Okay, and these are also the coefficients.
I mean, there will be several. Each kind of. Suppose we have A dagger r times and A n minus r times.
Hmm.
So those kind of numbers will be several times, and there will be several permutations of them. They will have same coefficient, I guess. So that's how.
But the question is like the coefficient here is 1 by n, right? So this symmetric term brings an extra 1 by n. So where did that come from as the question, I guess? Like that's the definition of that symmetric ordering, right? 1 by 2 times that, then that is 1 by 3 times this. So there should be 1 by n times the sum of all terms.
Okay. So, let us see what happens at n is equal to 1.
The same term is there.
L is equal to 1, R is equal to 0 and 1.
Hmm.
So,
So, this is matching.
yeah.
Okay. What about n is equal to 2? So, this will be minus alpha square, then a dagger square plus alpha star square a square, and then you will have minus alpha into alpha star, this is a dagger a, and then plus alpha star into minus alpha into a dagger. So, there should be basically, if I take this, then 2 should be here, right, is not it, because
That has 1 by 2. So
yes. So, this should be 2, right. Okay.
This matches with the binomial coefficient.
Yes. So, this is how we will basically, if you look at the binomial expansion, I mean these coefficients are there, I mean whatever you do, but if you look at the operators, once you take care of these coefficients, all are having same weight. Okay. So, therefore, there is no extra coefficient you will have. Okay, good. Is that clear? Okay. So, now that you have this expression, so now you can go back there. Yeah, so basically you can now write d of alpha. Oh, I have done it for d of minus alpha, but that is okay. Okay. So, d of alpha is equal to n is equal to 0 to infinity alpha a dagger minus alpha star a whole to the power n by n factorial. So, now if I use this, basically what you will have is, and I am not going to write it again and again. Okay. So, basically what you will have is yeah, now, but there is a trick here. So, let me write it first, and then r is equal to 0 to n alpha to the power n minus alpha star to the power alpha star to the power, I should be bit careful, let me call it as n prime and these as n prime. Okay. So, then things will be clear, alpha to the power n, alpha star to the power n prime minus n divided by n factorial, n prime minus n factorial, then a dagger to the power n, a to the power n prime minus n. Is that clear? You just use this expression in this thing. Is it okay? So, this n factorial will go away because of this, and then you have this term. So, I have just replaced this, where is this n? No, n should not be there.
Yeah, so maybe we want sum over n is equal to 0 to n, like maybe.
No, this is not r, this is n, sorry.
Yes.
Yeah. Okay. So, this is fine. I will just replace r by n. Okay. Okay. So, then, so this is your d. Now, I will do another jump here, and this hopefully you can follow. So, therefore, I will write d of alpha, here it is finite sum. Okay. So, I will replace it by infinite sum, n prime is equal to 0 to infinity, but now I take m is equal to 0 to infinity. So, basically I am calling this n prime minus m n as m, new variable m. So, this now I can write as alpha to the power n minus alpha star to the power m divided by n factorial m factorial a dagger to the power n a to the power m. Do you agree with me? Yes, because anyway this runs from 0 to infinity. So, in principle by replacing this by m I can also do that. Okay. So, this is my expression for d alpha in terms of symmetric ordering. We have seen expression for d alpha in terms of normal ordering, anti-normal ordering, and this is in terms of symmetric ordering. Look here, there is no exponential term which was there for normal and anti-normal ordering. Okay. So, this is the expression for d alpha. Okay. Now, you can invert this relation. So, you see that d alpha, of course, these are all finite, these coefficients, and one can prove that this series is convergent series also, that is not an issue, one can prove that. But the question is that how do I invert this? So, in other words, what will be a dagger to the power n a to the power m, this symmetric ordering in terms of d alpha. Okay. So, basically you will have to differentiate with respect to alpha and alpha star. Okay. So, what you can prove is that this partial derivative of d of alpha to the power n, d of minus alpha star to the power m at alpha is equal to 0, this is what we get. Okay. So, you can think of it like Taylor series expansion. Okay.
Regarding that step where we introduced m rather than
Yes, n prime minus n.
why does m go from 0 to infinity then? Why do you want from until n prime?
Yeah, because you see what are the values of n prime and n. So, n varies from 0 to n prime.
Yes.
So, therefore, n prime minus n can be 0 also when n is equal to n prime.
Right. Yeah.
But n prime can take infinite values also, it can take infinity. So, therefore, m also can take also infinity, right.
But won't there be a factor of half or something in that?
What of?
A factor of half.
Why?
Like for instance, like when we do this, the arithmetic of nearest neighbors sort of this calculation we do, that you sum over everything that's less than this number, and then you want to like take a total sum rather than just do less than, then we double count the indices.
Yes.
Similarly, isn't there a double counting going on? from
No,
that step to
no. What you can do is to prove this thing. Okay. So, what you can do is do not take this up to infinity, take it to be up to some finite value. Okay.
Yeah.
And then you prove that these two expressions, this is fine, this is up to n, and now we will have to see what is the maximum value m can take. So, n can be 0. No, this can I write it maximum value m can take up to capital N?
Yes.
I'm not entirely, I have to think more about it.
Why? Because you see this is your n prime minus n, right.
Yes.
So, n prime, when n is equal to n prime, this is 0.
Well, the thing is, n prime itself is going from 0 to infinity, right? So,
Right.
if we expand it, so n prime would be 0 first, then n will be only 0. N
Yes.
prime when it's 1, then n can be 0 and 1.
Yes,
N prime is 2, it can be 0, 1 and 2. So,
Yes.
like that, like, the thing is, n is always less than n prime. Less than equal to.
less than equal to n prime.
Yeah,
Yes.
but here, like, for instance, I can have a term where m is, 3 and n prime is 2.
Okay. So, let us do this.
But maybe I can do it at home.
Yeah, I think you can, what you can do, you can expand
Yeah.
taking up to finite terms,
Yes, yes,
and then you can equate this thing.
yes. I'll try to do that.
This we will have to think about whether this will be n or something else, but some finite value.
Yeah, but having a factor of half would probably fix the problem. That
No,
I see.
there should not be any factor. Okay.
Okay, okay.
Yeah, there should not be any factor. Okay. As far as I understand, this, there should not be any factor there.
I'll think about it.
Yeah, sure, sure. Okay. Okay, good. So, in fact, this is the, I mean, if this is valid, then this is also valid.
Yeah.
Okay, good. So, who is there? Okay, good. So, now you can look at the symmetric. So, this is now symmetric ordering. I have not told you about the coefficients. So, f is equal to n m is equal to 0 to infinity b n m a dagger to the power n a to the power n. So, this is my symmetric ordering. Okay. Right. So, now again we have these expressions. So, we have already written this thing. Let me erase this part. Okay. So, now what you can do is you write this expression for d of minus alpha. D of minus alpha will be, what was the expression I mentioned just now? N m is equal to 0 to infinity. What was this thing? This is alpha to the power n, and then minus alpha star to the power m, n factorial m factorial. This is a dagger to the power n. Sorry, minus alpha, this is plus alpha. Yeah, right. So, this is your d thing. So, you then insert it here. Okay. And as usual, if you insert it and then compare it, what you will see is that, so basically this will tell you that b n m is equal to 1 upon n factorial m factorial 1 upon pi alpha belonging to c d square alpha trace of f d alpha minus alpha to the power n alpha star to the power m. Okay. So, this is like generally this would converge, although we do not have this exponential of minus mod alpha square of term. Generally this would converge, and for what sort of functions? So, this is weight function. So, for what sort of weight function this will converge? Basically for those weight functions for which these moments are finite. Okay. Right, because these are the moments of such weight functions. So, if the moments are finite, then your weight function will, I mean basically this will be also finite. So, you see that for a bounded operator, the coefficients corresponding to this, so this coefficient C n m, which we considered earlier for the normal ordering, these are more or less finite, almost for all bounded operators. Here there will be some bounded operator for which this may not converge, I mean this may not be finite. So, the thing is that for those weight functions for which this integral is finite, and this integral finite means for those weight functions for which these are all what are these? These are basically called moments. Okay. So, these moments are finite. So, these are the moments of this weight function.
I mean we are integrating over alpha.
Yes.
And over the entire plane, complex plane. So alpha star, alpha, I mean, they will be over. So there will be, I mean, they will reach infinity.
Yeah, you will have to, basically when I say moments are finite means you will have to take mod of these and then use Schwarz equal to all those things. So basically this, when the moments are finite means this integral is itself finite for all n and m.
The whole integral is what we call.
Yes, whole integral is that is the moment of that weight function. Okay, good. So you see that for single, I mean even if f is bounded operator, these coefficients are generically bounded finite, but this coefficient may not all be finite. Okay. So, the scope is, I mean finiteness of the coefficient will be less probable compared to finiteness of these coefficients. Okay. But more or less for for useful bounded operators this will be also finite. Okay, so let us take this example. So, I take f is equal to alpha beta. You can also take f is equal to this nm are the number operators. Okay. So, f is, this is trace class, right. Do you agree with me? This is a trace class operator, right. Similarly, this one, this is also trace class operator. Okay. And so, if you look at the weight function trace of f d alpha for this, so this is basically beta. Oh, I have taken alpha, let me call it gamma. Huh? So, beta d gamma alpha. Okay. And of course, this is you can calculate this, I am not going to do that. This is minus mod gamma square by 2 plus gamma beta star minus gamma star alpha. Okay. So, this is your weight function, and from there you can figure out that what about this CNM. So, when I write CNM, this is for normal ordering coefficients. So, if I look at that, this is n factorial m factorial 1 upon pi gamma belonging to C d square gamma trace of f d gamma, then e to the power minus gamma square by 2 into minus gamma to the power n gamma star to the power n. Okay. And if you put this expression, you see that basically, I mean if you take these two together, you will have a factor of e to the power minus gamma square, right, and everything else will be finite therefore. So, therefore, this value will be finite. Do you agree? Yeah, this will be finite. Okay. So, for this is for this trace class operator, this is all finite.
It will be again like some Fourier transform. So alpha beta star minus alpha. Oh no,
It is not a Fourier transform. No. Okay. Similarly, you can show that if I look at this BNM, which is 1 upon n factorial m factorial. So, this is corresponding to, so this is for normal ordering, this is for symmetric ordering. So, this is 1 upon pi gamma belonging to C d square gamma minus gamma to the power m gamma star to the power n gamma star to the power m exponential of minus gamma square by 2 plus gamma beta star minus gamma star alpha, because you know you do not have this term here, only this one. Still this is finite because of this term. Okay. So, therefore, for this trace class operator, both the coefficients corresponding to normal ordering as well as coefficient corresponding to symmetric ordering are both finite. Okay. But now, if you calculate the coefficient corresponding to, so this is anti-normal ordering coefficient d n m. So, this is 1 upon n factorial m factorial into 1 upon pi, this is gamma belonging to c d square gamma trace of f d gamma. So, trace of f d gamma we know what will be this for, and then e to the power gamma square by 2 into minus gamma to the power n gamma star to the power m. So, now you put this expression here. So, this minus gamma square by 2 and this gamma square by 2 will get cancelled, and therefore, you know you will have basically divergent integral. Okay. So, therefore, this will be singular. In fact, what you can show that these are something proportional to derivative of delta function, higher order derivatives of delta function. Okay. So, you see that this simple minded operator, for this simple minded operator, this anti-normal ordering does not make sense. Now, this will be unbounded basically, or divergent, whatever you want to call. Same is the case with this operator also in this basis.
Why is it divergent?
Yeah, because you see this, if you put this expression, what will you get? It is 1 upon n factorial 1 upon pi gamma belonging to c d square gamma, then minus gamma to the power n gamma star to the power n exponential of gamma beta star minus gamma star alpha. What will be this integral? Is it a convergent integral? I mean, you can express it in terms of real and imaginary parts. Okay. It will not be, because you know here you will have modulus of gamma powers of that, and then this is, there is no square here, this is something like so this is basically in first order in gamma. So, this will not help you.
That exponential is even worse than the polynomial.
Exactly, yes, even worse than the polynomial, yes.
Oh, in CNM there was minus
Gamma square,
so it will just
it will reduce, yes,
Plus gamma square.
dominate the term.
dominate the term, yes. Okay. Right. Okay, good. So, therefore, and as I said, same is the case for this operator also. Okay. Right. Okay, then. So, let us now look at some interesting. Okay. So, I have not talked to you about the convergence of this operator sum. You know, I have considered this trace f as a normal in the form of normal ordering, in the form of anti-normal ordering, symmetric ordering. Then one might say that f is of course bounded operator, but the series for the expression for normal ordering or anti-normal ordering or symmetric ordering, it contains infinitely many terms, right. So, like when I write f as n m is equal to 0 to infinity c n m a dagger to the power n a to the power m. This is bounded, that is fine, but what is the guarantee that this itself converges? See, even if these terms are finite, it does not mean that this will converge, right. So, you will have to talk about convergence of this series itself. Okay. Now, this being operator, there are different notions of convergence. You can say strong convergence, that means you know you can take n is I mean n is equal to 0 to capital N, m is equal to 0 to capital M, or maybe both of them n, it does not matter. So, C n m a dagger to the power n a to the power m. So, call it as something like S n m, this operator, and say that f minus S n m norm of this goes to 0 as n and m both goes to infinity. So, this is in the strong sense, okay. In the operator sense this should converge, but that is quite strong, that may or may not happen. So, what one can look at is whether in coherent state basis I can claim this, that this expression, and now I take this. So, this is a finite quantity because f is bounded, whether this series is a convergent series, okay. And if it is convergent for all alpha and beta, then I can say that yes, f is equal to, I mean f is equal to this series. This is called weak convergence, but that is okay. So, now the question is whether this series is convergent. This is a series of scalar quantities, whether this will converge or not, and this is not difficult. You can, this is basically n m is equal to 0 to infinity C n m. What about this? This is alpha star to the power n, alpha beta to the power m, right, and then you can take this as alpha beta, okay. So, now we need to look at convergence of this series, okay. So, yeah, so basically what you need to look at is, sorry I am a bit messy about it, but this is which is this series n m is equal to 0 to infinity C n m alpha star to the power n beta to the power m, okay. So, convergence means that if you can prove that this sum is an analytic function of, so this is analytic function of alpha star and beta, because these are two variables. If this is an analytic function, then of course this is a convergent, and so therefore it will converge to this value, right. So, let us not go into all those details, let us assume that this is analytic and all that, okay, right.
If this series is analytic.
Yeah, this series has to be analytic function. Okay, good. So, let us now take an interesting example where you can talk about normal ordering, anti-normal ordering as well as symmetric ordering all together. Today I should be careful. What is the time now? Oh, still we have time, okay, because there is a talk here, okay. So, let us take these examples. This is quite interesting example and quite useful also. So, let us take, this is a complex number lambda, any given complex number, and let us take this operator f lambda is equal to lambda to the power a dagger a. I mean this is very typical, what does it mean? So, this a dagger a, it can take eigenvalues, integer eigenvalues, right. So, therefore, this you can say that this f lambda can take values powers of lambda, integer powers of lambda, right. In other words, I can write it as exponential of a dagger a times log lambda with respect to base e. Now, this is of course complex logarithm. Okay. So, I should write capital L, but that is okay. So, from here you see that, I mean, this is a complex logarithm of course, but this is the way you define this operator. So, for example, if I take this one, so let us say lambda is equal to minus beta h cross, what is that, omega by k b t. So, this this beta h by k b t, right. This is the this by the partition function. This is your thermostat, right. So, it is something like this. Okay. So, sorry.
This is ln lambda minus beta square.
Yes, this should be ln lambda. Yes. Okay, this is your thing. Yeah. Okay. So, for this operator, so let us see what.
The KBC, right? A that beta 1 by 2.
Sorry. Yes, you are right. Yes. So, yeah, it should not be minus beta. Yeah. Okay. So, now if I look at this f square, f of lambda square. So, this is trace of f lambda dagger f lambda. Okay. So, this is trace of exponential of a dagger a log, I think it is better to write ln lambda, right. Every time I should not write a log e lambda, etc. So, ln lambda star times exponential of a dagger a ln lambda. Okay. This is how we will have, and this is what, this is basically trace of exponential of 2 times real part of ln lambda times a dagger a, right, isn't it? Yeah. So, this is n is equal to 0 to infinity exponential of, because a dagger twice n real part of ln lambda, right, and then you can sum it, it is a geometric series. This is 1 by 1 minus e to the power twice real part of ln lambda, provided magnitude of this is less than 1. Okay. So, which is, so e to the power twice real part of ln lambda is less than 1. Okay. Anyway, so therefore, you see that f lambda is bounded if lambda mod lambda is less than 1. Okay. Right. So, this is a bounded operator provided you take mod lambda less than 1. Okay. Next, you can take this norm, which is trace norm. Okay. So, you can do everything whatever I discussed. You can show that this is finite. So, which means f is a finite operator. This is finite means this is finite operator, right. Okay. Provided, so this is also oh no, sorry, not finite, sorry. Yeah, this is finite means that the trace norm is finite. Okay. F is not finite operator, F finite operator in terms of F1 norm, okay, 1 norm. So, this is finite means, so this is finite provided again lambda less than 1 magnitudal lambda. Okay. I mean as usual you define this F2 is equal to square root of this least upper bound, no, not F2 is this trace of square root of F lambda dagger. So, I will call it lambda F lambda, right. This is your F2. So, you can show that this is finite provided this is less than 1. And interestingly, you can show that this F1 norm, which is the supremum norm, this is finite if your lambda is less than equal to 1. Okay. So, again you can use the definition and figure out that this is the case. So, therefore, you see that this operator for magnitude of lambda less than 1, this is bounded, this is trace class and also finite. Okay. Right. Okay. So, let us look at the weight functions. So, I am looking at trace of f of lambda d of gamma, okay, which is trace of lambda to the power a dagger a d of gamma. So, this is my weight function. Okay. So, I am not going to do it explicitly, in principle you can do it, but what I am going to do.
This relate to the convergence.
Which one?
Well, this is different. Okay. I mean,
No.
I was thinking that you were relating it to the convergence of F1.
No, that will come later. First, we will have to understand boundedness of these operators. Okay. So, this is bounded within this range. This is also of course trace class within this range and finite within this range. Okay. Right. So, you can show that actually this f lambda satisfies this differential equation a dagger f lambda a. Okay. So, from this definition f lambda is this one. From this definition you can show that f lambda satisfies this differential equation. Okay. I mean this is not very difficult. What you should do is you should use this formula. If you take f and some function of operators of a dagger a, I mean a times a dagger a, so it is like number operator. Okay. So, this is g of a dagger a plus 1 times a. So, you will have to use this formula to get this. Okay. Right. And this is something like normal ordering, because you have a dagger on the left, a on the right. Okay. So, and of course, you have the initial condition that f of lambda is equal to 1. What is that? Lambda is equal to 1. This is 0 identity, right? Okay. So, if you use this condition, okay, here in solving this thing, so what you will see is the following, that f of lambda, so solution, and this is what we will use quite often, that this is exponential of lambda minus 1 a dagger a. Now, you may say that look, this is already the expression for f lambda, right, already the expression for f lambda, which is like this. But if I write it in series form, this is not normal ordering, right, is not it, because it will be a dagger a square, I mean a dagger a to the power n by factorial n kind of. So, that is not normal ordering. But if you want to write, oh yes, what is the time? 3:30, right? Yeah, I will finish by 3:20.
Take your time.
Yeah, sure. Yeah. So, now if you take, so this you can write as sum over n is equal to 0 to infinity ln lambda to the power n a dagger a to the power n by n factorial. This is not normal ordering, neither normal ordering nor anti-normal ordering, anything. But if you solve it using this initial condition, what you will get to see is this one. This, if you write it in this series, this is not normal ordering, but this symbol colon, okay, it means that you are actually using normal ordering here. Okay. I mean, if you want, you can express things. This will be, this is quite difficult, write it in terms of normal ordering. I mean, powers of a dagger and then powers of a.
How is this differential equation being solved? How to begin solving this kind of equation?
Yes. So, okay. So, what you can think of is basically you can start from here, okay, and then you can try to solve it perturbatively. Okay. So, of course, this condition is satisfied, right, is not it? What about this? Oh no, I don't know. I mean, what about f lambda d lambda? So, basically what you can do is yeah. So, this means that you will have to do it perturbatively. Okay. So, in the sense that let us say I take first this one, okay. So, identity plus lambda minus 1 a dagger a, this by factorial 1, and so then, so basically if I take this one and put it here, what will I get? On the left hand side, what shall I get? A dagger a. On the right hand side, lambda, no, what will I get in the right hand side? A dagger a plus lambda minus 1 by factorial 1. This is a dagger square a square, right? Okay. Of course, this is not equal. Yeah. So, what you can do is
So there is this method of solving differential equations of this kind where you just assume that f lambda is exponential of lambda times some function.
yeah, but if you do, that is the way you do, but you should be a bit careful because you will have to use this normal ordering.
How did you get a dagger in LHS?
Yeah, because if you you take this part, this is, let's say this is your f lambda for small lambda. So I am taking only first order term, right?
Okay, if I take the second order term also
Yeah.
and then differentiate df d lambda,
Yes.
then maybe I will get the second term here.
Exactly. Yes. Yes. Yeah. So if this is just a scalar quantity, right, then I know how to solve it. Okay. So this, because this is okay, so this is actually so this is normal ordering I am talking about, because this term is here and this term is here. What you need to do is when you look at the solution, you will have to express it in terms of normal ordering. Now this is a bit tricky issue, this I write it fine. What it means that you will have to express it in the normal ordering form, not just this one. Okay. In fact, perhaps this may be useful. Let me see. So what I am looking for, which is a dagger A, what I am looking for is Nm is equal to 0 to infinity Cnm lambda a dagger to the power n a to the power m, right? This is what we are looking for. So now you can actually input this there in this equation. Okay, and then what will happen? So on the left hand side, so df lambda d lambda, what will be this? This is, so here of course I am assuming that this is less than 1. Okay. So this will be 0 to infinity d of c n m lambda d lambda a dagger to the power n a to the power m. This is your left hand side. And what about right hand side? Right hand side will be n m is equal to 0 to infinity c n m lambda a dagger to the power n plus 1 a to the power m plus 1, right? Okay. And now you will have to equate these two, the different powers of this thing.
And we will get the solution for Cn lambda and from
In principle, we will get, yes.
if we compare the coefficients.
Yes.
D Cn lambda. Achha, okay, so this will be coupled differential equation.
Will it be coupled?
Because d Cnm lambda d lambda
Mm-hmm.
will be equal to some Cn minus 1 m minus 1.
Yes.
Okay, yeah, but also you will have to use this condition that f of 0 is equal to identity.
So the initial
So it means that c 0 0 0, right? This should be equal to, no, what does it mean? F 0 is equal to identity means what?
Cnm of 0.
Yes, Cnm of 0, sum over all the terms is 0.
No, no. If I take lambda is equal to 0 here, so Cnm 0.
That just means Cnm 0 is 0 for all terms.
No, it's a dagger to the power n.
Yeah, that's also there, and that should sum to 1.
Yes, that should sum to 1. Okay, so basically it means that nm is equal to 0 to infinity a dagger to the power n a to the power m. This is equal to identity, right? Okay. But how can it happen? What should be the values of the Cnm then? Basically, for all other nm, the coefficient should be 0, isn't it? See this identity a dagger, sorry, this should be a dagger to the power n. So, oh, okay. Yes.
No, I was just saying So we want to argue that only diagonal terms are non-zero, something like that.
No, no. See, this has to be identity, right?
Yeah.
Now, this kind of operators a to the power n, a to the power m, when n and m are not all of them are 0, not both of them are 0. This, independent of identity. This is, you cannot express identity in terms of this or vice versa. So,
Okay, so those coefficients, non-diagonal ones have to be.
so basically, so therefore, what you will have is this is 1 and C n m 0 is equal to 0 for all other n m.
I mean, if n is equal to m, then maybe it can still be non-zero, right?
Why? N is equal to 1, m is equal to 1.
Yeah, n equal to 1, m equal to 1, or n equal to 2, m equal to 2.
Why? Because then it is,
Otherwise, what we have is like if C 0 0, okay, then FC, okay, maybe, yeah, I'm not entirely sure.
no, see, the thing is, look at here. As I said, these operators for different values of n and m, they are independent operators.
That's a number operator, right, for n equal to m.
Yes, number operator, number operator.
Number operator. It's
Yes.
number operator is whole to the.
Yes. So, therefore, this, so basically what will happen is where so you will have to use this initial condition and then you will have to equate these two.
Maybe even simpler than
Maybe other simple a process will be there.
substitute the solution into the
Yes,
equation
yes.
and verify that it's
Yes.
satisfied.
Yes,
I mean, often in differential equations we just guess the solution and then put it
exactly,
back and
exactly.
find that it's
This is a guess solution actually, this is a guess solution. This should work there. Anyway, this is okay. So basically, so this is your normal ordering, but what is important, more important is you can figure out, I think I have given the expression for CNM, right, for arbitrary operator, isn't it? I have given that. So you can figure out from there that CNM is equal to delta NM divided by n factorial into lambda minus 1 whole to the power n. Okay, sorry, I should stop it here. So this is the coefficient. Now this you should verify by the expression of CNM I mentioned earlier, this integral expression. For bounded operator that should be valid, and this you know that this is a bound, where is that? Lambda to the power a dagger a is a bounded operator for mod lambda less than 1. So you can use that to figure out that for normal ordering this is the coefficient, and this is finite. Okay, good. So yes, and okay, good. So you see that for that operator, of course this is expected that this coefficient for normal ordering should be finite. We will show that for the for this symmetric ordering also the BNM is finite, and for the anti-normal ordering there is certain range of lambda values for which it will be finite, the coefficient. We have seen generically for unbounded operators, even for bounded operators, the coefficient for the anti-normal ordering are generally not bounded, but for this operator we will see that for certain range of lambda values the coefficients are finite for the anti-normal ordering. And so that will be the end of the story.